In June 2023, a submersible called the Titan was descending toward the wreck of the Titanic when, in a fraction of a second, it ceased to exist. Investigators later confirmed it imploded under the crushing pressure of the deep ocean. A failure so fast that the 5 people aboard had no time to perceive it happening. It's a terrifying case. But here's what almost nobody talks about. Submarines have been diving into those exact same crushing depths for over 100 years. And the vast, overwhelming majority of them have never imploded. So what's actually standing between a submarine and the ocean trying to crush it? The answer is one of the most underrated feats of engineering on the planet. Water is heavy. At the surface, the air around you is pressing down at about 1 atmosphere, roughly 14.7 pounds per square inch, something the human body is so used to that we never even notice it. But for every 10 meters you descend underwater, you gain another full atmosphere of pressure on top of that. The deeper you go, the faster that number climbs. By the time you're at 4,000 meters, roughly the depth of the Titanic wreck, the water is pressing in at around 400 times the pressure you'd feel standing on dry land. To put that in perspective, that's roughly the equivalent of stacking a small car on every single square inch of a submarine's outer hull, all at once, from every direction. Submarines don't avoid this pressure. They sit directly inside it, fully submerged in the exact environment trying to crush them. The entire engineering challenge of a submarine, arguably more than propulsion, more than navigation, more than anything else, is keeping a pocket of normal, breathable, sea-level pressure alive inside a shell that has the ocean trying to collapse it from every direction, all at once, for as long as the vessel remains underwater. The first trick isn't the material, it's the shape. Submarine pressure hulls are built as cylinders with rounded or spherical end caps, never as boxes, and never with flat, irregular panels anywhere on the crew compartment. Here's why. Pressure from water pushes equally in every direction at any given depth. A cylindrical or spherical shape distributes that force evenly across the entire surface, with no flat panels and no sharp corners where stress can concentrate into a single weak point. Flat surfaces are mechanically weak under this kind of load. When you push on a flat panel from one side, it wants to bow and buckle inward, the same way a flat piece of cardboard collapses far more easily than a rolled-up tube under the same pressure. A sphere, by contrast, is the strongest possible shape against uniform external pressure, distributing the load so evenly that there's almost nowhere for a weak point to form. That's part of why many of the deepest diving research submersibles in the world, vehicles designed to reach the very bottom of the ocean, use spherical crew compartments rather than the classic cigar-shaped hull most people picture when they imagine a submarine. Shape alone isn't enough. The hull also needs a material that can absorb enormous compressive force without cracking or deforming permanently. Most military submarines use high-strength steel alloys, refined specifically for this purpose since World War II. Some designs, like several Soviet-era submarine classes, use titanium instead, because titanium offers a higher strength-to-weight ratio, letting engineers build a hull that can dive deeper without becoming impossibly heavy. But here's the part that matters most. Switching to a stronger material doesn't simply multiply how deep a submarine can safely go. The relationship isn't linear because failure under deep-sea pressure is usually driven by buckling, the structure folding or collapsing inward, which depends on the geometry and stiffness of the hull as much as the raw strength of the material itself. A thicker, well-shaped steel hull can outperform a thinner, exotic material hull that wasn't engineered with the same precision. This is one of the exact areas where the Titan's design diverged from convention. Its hull combined carbon fiber composite with titanium end caps, a material combination that, according to the official investigation, had never been fully validated for repeated dives to those depths and showed undetected damage building up over time. Every certified submarine in operation isn't designed to survive only its intended operating depth, right up to the exact moment it would fail. It's designed with a substantial safety margin built in from the very first calculation. Engineers determined the theoretical crush depth, where the hull would actually fail under pressure, then deliberately set the maximum operating depth dramatically shallower than that number, often by a wide enough margin that a vessel could exceed its stated limit and still survive. This is paired with rigorous, repeated testing before a vessel ever carries a single crew member. Hydrostatic pressure tests that simulate dozens of dives beyond the maximum depth the submarine will ever actually be used for in service. X-ray inspection of every single well joining the hull together, and oversight from independent classification societies. Organizations whose entire job is to refuse certification if anything, anywhere in the design or construction process falls short of established engineering standards. It's slow. It's expensive. It can take years before a single new submarine design is cleared to carry passengers or crew. And it's the exact process that gives a roughly 70-year-old design philosophy a near-perfect safety record across hundreds of thousands of dives by submarines all over the world. When submarine hull failures have happened throughout history, investigators almost always trace them back to one of a few specific causes. Welding flaws that weren't caught during inspection, corrosion that weakened the hull over years of service, battle damage, or, as with Titan, a design and testing process that skipped the rigorous validation every certified submarine is required to go through. In other words, implosion isn't some unpredictable freak event. It's almost always the predictable result of a hull either not being built to the standard or not being tested the way the standard demands. The ocean at depth is one of the most hostile environments on Earth. More people have actually traveled to space than have reached the deepest points of the ocean floor. And yet submarines have been operating safely inside that crushing pressure for generations, carrying crews of hundreds on routine missions that never make headlines precisely because nothing goes wrong, not because the ocean got any gentler, but because the engineering got rigorous enough to match it, dive after dive, decade after decade. The Titan tragedy wasn't proof that deep-sea travel is inherently too dangerous for anyone to attempt. It was a reminder of what happens when a vessel skips the very process, the testing, the certification, the safety margins that makes every other submarine on Earth come back up safely.